Hi, I'm Aaron. Thanks for coming to my talk. I'm going to be talking about learning to model another agent's beliefs. This is preliminary work. It's a short paper here. What's the broad idea? The big idea here is we want to use logic-based knowledge representation tools to model the beliefs of an agent, and then we want to combine this with a learning operation. So we want to learn how an agent changes their beliefs when they get new information. So specifically, we're going to talk about belief revision operators from knowledge representation, and then we're going to talk about classification algorithms from machine learning. And our sort of motivating example is kind of a silly picture I have here, but imagine you have a robot and their job is to feed some human, and they know something about the food. They know that the temperature of the food might matter, the color of the food, the smell of the food. These might all determine what the human's going to eat. But they might also change their mind. And what the robot needs to do is it needs to figure out, okay, so one day they ate this food, the next day it was red and they wouldn't eat it. So how did the fact that the food is red change their beliefs about whether the food was going to be good or not? Right? This is the kind of example that I have in mind. But basically, the idea is any kind of general intelligence. You need to be able to have a model of how somebody else changes their mind in response to new information. So I don't want to go into really preliminaries because this is a general intelligence talk. So I'll just say quickly, the theory of belief revision, the dominant approach, is called the AGM revision. And this picture won't make a lot of sense, but the idea basically is anytime a rational agent revises their beliefs, what they really need is an ordering over all the possible configurations of the world. So they have the things they believe most likely in the middle, and then they get successively less and less likely things they believe. So when you get new information, what you should believe is if the new information is good, you should believe sort of the most plausible things that were in your original ordering that are consistent with the new information. So that's where this arrow points. And this is a well-developed theory from late 80s is when this really started to develop, and it's been really highly effective in the knowledge representation community. The other thing I'll have to talk about a little bit is machine learning. And the approach that we really use in this paper is called ID3. And ID3 is a machine learning approach where you basically learn to classify new instances of data by building a decision tree. So the idea is you say, I have a bunch of data. So when it's hot and sunny, then this agent I'm observing plays tennis. And when it's rainy, they don't play tennis. And from these basic instances, I learned to classify new instances that aren't in my original data by building a decision tree like the one in the picture here. So those are the two main sort of theoretical frameworks I'm looking at. And the basic question that we're trying to address here is we want to learn how an agent revises their beliefs. So what we want to do is we want to look at a bunch of instances in the past. So we say in the past, when they had a certain set of initial beliefs, and then they learned that the food was green, then they didn't eat it. And another time they had some certain beliefs, and then they learned that the food wasn't beef and it was hot, and then they did eat it. And we want to learn how they make these changes to their beliefs based on new income. If we get a new example, like, okay, so what if we give them something that's not beef, and that's all we know? Are they going to eat it or not? Like, well, that's the kind of process that we're trying to figure out. And our framework here is really, it's a really pretty formal framework. It's in propositional logic because that's the framework for belief revision. So you have a goal sentence, G, and your goal sentence is basically the thing you want to know if they're going to believe it or not after revising. And then your instances now are sort of positively or negatively labeled conjunctions of literals. So they're big formulas. And something like an L plus means after revising by L, they believe G. Whereas L minus would mean after revising by L, they do not believe G. And that's the basic setup that we have. So what we've done in the paper, and again, I encourage you to take a look at the paper. We've done in the paper is we've described a very simple software system that we've created that will check the agreement of a set of instances with a specific revision operator. So what the software does is, as input, it takes a bunch of instances. So that's just how the agent revised their beliefs in the past. It takes an initial belief state, and it takes a goal sentence. And the process it goes through is from the initial instances that you have as data, it runs the ID3 algorithm, it builds this decision tree for classifying new instances, and then it compares that tree and it checks for every possible conjunction of literals. It checks, does the decision tree classify L as positive exactly when revision by L entails G? That's the idea. And if both answers are yes, then this whole system returns true. So that's a very abstract version. So what does it really mean, though? What are we really saying? What we're saying is, if the decision tree agrees with some revision operator, right, on a goal formula, when that means that the revision operator star here actually could be the revision operator that the agent uses to change their beliefs, right? So the instances are just what they did in concrete cases. And what we're trying to do is extrapolate from that, generalize and say, okay, so what is the revision operator they're going to use? Because if we have the revision operator, then we can actually figure out what they'll do in new instances. And we're trying to learn the revision operator by doing this simple classification of new instances and then finding all revision operators that are consistent with this classification of new instances. So what this lets us do then is it lets us say if certain revision operators are actually in this set I star. So I star is just the set of revision operators that are consistent with the instances we have, with the data we have. And then what you can do, well, okay, so first of all, how do we actually check this? Well, this is actually pretty hard. We have to use a pretty high-speed belief revision solver to do this efficiently, which we've developed for other reasons. We have a really fast, efficient belief change solver, and it can solve for a certain class of revision operators. It's really expensive, but what we can do is we can check for every one of the revision operators in this class, whether or not it's consistent with the data we have. And then what does that mean? Well, it means we can draw conclusions about how the agent may or may not be actually revising their beliefs. So what that means is, given a set of instances and a goal G, we could be asked, does the agent believe G after revision by some formula? And there's a bunch of answers we can give. We could give a skeptical answer where we say, well, they will believe G if they actually believe G every time we test the revision with one of the revision operators in I star. Or we could do credulous reasoning. We say as long as it holds for some revision operator. Or we could do some sort of democratic variation. But the idea is what we now have is a method to go from instances of past revision to here are the possible new belief revision operators that we could use. Okay, so why does this matter for artificial general intelligence? Well, I'll say, first of all, it matters because rigorous models of knowledge and belief are sort of really well understood in the KR community. They've been studied. We have proofs and we have models and we have verification that they work and we've got efficient solvers and we've got a lot of arguments for why they actually capture something useful. And in the machine learning community, they just really aren't used. So if these models really capture some formal aspect of reasoning and learning allows us to draw conclusions from data, we should be able to combine these two things to get much more powerful reasoning systems. We want to be able to combine these systems so that instead of just learning to classify instances in kind of a flat way like the ID3 algorithm does, what we want to do is learn the mental state of the agent, learn what the operation they use is when they incorporate new information. If you can learn that, then you can actually do a lot more powerful general intelligence things because you're no longer just classifying new instances. What you're doing is you're figuring out how somebody thinks. That's the idea. And then, this is a short paper, so it's a short talk. In conclusion, I'll just say, what did we do here in this paper? And again, it's very hard to introduce the ideas in the paper so quickly. What we did is we introduced an approach for learning revision operators from data. Given data about past revision, here's the revision operators you could use. We're bringing together techniques from the knowledge representation and the machine learning community, which I think is an important goal of the AGI community, right? We want to actually combine all of the things we have to get sort of robust models of human-like reasoning. And the focus here is really on how beliefs change in response to new information. It's about learning the mental state of an agent and the way that that mental state influences the things they believe when they get new information. I said this is actually ongoing work. So this paper is really just a preliminary view of what we're doing, but ongoing. We're optimizing the revision solver. We're making it faster. We're making it work for a wider range of operators. We're exploring different learning models. So ID3 is just one category of learning models. We're looking at now linear regression, and we're looking at some deep learning models to see if we can get better results. But in every case, the idea is the same. We're trying to get people to, instead of just learning the action to take or learning the classification to make, use all this data to actually learn the mental model that an agent uses to revise. And in this case, the mental model is based on a very well-known belief revision system called AGM. Okay, and that's it. Thanks, everybody.